created did have this title, which is quantum theory, and I'm going to bring things down to earth after that exhilarating survey of the state of the art. We're going to be dealing here not even with gravity, we're going to be dealing with n-particle Galilean variant quantum theory. So I'm just going to jump right in. I assume everyone has some familiarity with that framework if you're here at a quantum gravity conference. So here's the problem. Ordinary quantum mechanics provides assignments of probabilities at a particular instant of time. We've got this interpretive framework where, in a pure state, I'm talking here about the Dirac von Neumann formalism, the expectation value of an observable is given by this in the Schrödinger picture, by this in the Heisenberg picture. They give the same number. Yet quantum gravity seems to demand a quantum theory without dependence on the time parameter. So here's this question: how do we provide a meaningful assignment of probabilities that doesn't depend on this classical time parameter? So the project, and this is something which people who work on quantum gravity have engaged in, is to reconstruct ordinary non-relativistic quantum mechanics such that explicit reference to T is avoided, and it wants to be in a way that lends itself to further generalization. So there are these two approaches that I'm going to concentrate on today. They seem to be opposed, and I'm going to say that they're actually really the same thing. So there's this option one, eliminate time, Gambini, Auto and Pullin. They try to avoid reference to a time parameter entirely by just not talking about time. And we're going to phrase the predictions so that they don't refer to times at all, and we're going to interpret these things in terms of conditional probabilities. So that's option one. Option two seems to be very differently situated. We're going to promote the parameter t to an operator, to an observable t, and predictions are going to be referred to the values taken by this observable, a time observable, but also we're going to interpret this in terms of conditional probabilities. So I'm going to argue, step by step, that these take us to the same place, which I'm going to call extended quantum mechanics, extended quantum theory, and then hopefully in the last part of the talk I'll explore the consequences of taking seriously a proposal of Brunetti, Friedenhagen and Hogue, which goes beyond this formalism. So the motivation for doing this is Carlo Rovelli's relativistic mechanics. So he thinks that the way to approach this problem is to reconstruct classical mechanics so that we don't need to make explicit reference to a time parameter, and then we're going to sort of quantize the theory that results. So just very briefly, so in this framework of relativistic mechanics, a dynamical system is just described by a pair. So we've got a configuration space, a Hamiltonian. This is the extended configuration space, I'm going to call it, and a Hamiltonian mapped on the cotangent bundle, this extended configuration space. And a point in the state space corresponds to an orbit of the pre-symplectic form defined on the constraint surface, which is given by setting the constraint to 0. And an orbit, i.e. a state, defines the subspace of C. A dynamical motion, in our case, is just going to be a one-dimensional subspace of the curve. Okay, so let's look at a very simple example. We've got a free classical particle, and so our extended phase space we get by including time in our coordinates. So we've got this nice Cartesian product of the real line with the usual configuration space. The Hamiltonian is just the sum of our conjugate momentum to time, pt, and the ordinary Hamiltonian here. And the constraint surface is going to define these dynamical motions, and they're going to be parameterized curves which depend on t and q, but we've got this parameter tau which sort of counts as we go along the curve. And so Carlo Rovelli calls these the partial observables, and what the theory is tasked with doing is determining the correlations between these observables as we go along the curves. And we've got a very simple theory here. So t is a function of tau, it's just tau. Q is just the usual initial position plus v tau. The momentum is constant, it's free particle. The complete observables are those that commute with the constraints. So the Poisson bracket of an observable has to be 0 to be a complete observable. So the momentum's time independent, so that's going to be a complete observable. So that's just, initial data. But we can also define the initial position in terms of these tau-dependent quantities, and that's also a complete observable. And this fits in with the idea we just need to pick out the initial data, and then that gives us a point in the state space that gives us an entire orbit, an entire dynamical motion. Okay, so what do we do when we quantize this theory? Well, first we construct an auxiliary Hilbert space, so-called. So let's just say L2 functions of our extended configuration space. We promote the Hamiltonian constraint to an operator. This is just a simple example. And the physical states are going to be defined as those that are annihilated by the Hamiltonian constraint. Its operator size, our state, set that to 0. There's a bit of a mathematical hiccup here. The Hamiltonian has a continuous spectrum, which means that this constraint is going to be satisfied in a distributional sense. Another way of saying that is that the states aren't actually in our Hilbert space. They're like the Dirac deltas of position that don't lie in the Hilbert space. But we can construct a rigged Hilbert space, a Gelfand triple, and the states are going to lie in the dual of the Schwartz space, which is a subspace of a Hilbert space, which is like the space of smooth functions. And then there's this recipe for constructing a Hilbert space for these states, so a new Hilbert space, and the Dirac observables that commute with the constraint can be defined, like the complete observables can be defined on this space. And one of the questions I'm going to look at is just how does quantum mechanics look on this extended Hilbert space, this one, before we do this quantization procedure. So the sort of question we usually ask in ordinary quantum mechanics in this framework is going to have the form, what is the value of a partially observable given that the time is t, or that the time is tau, rather. So we can define a one-parameter family of these sort of promoted operators, so the big Q's are going to be operators now, and we can parameterize them. So I've got T here, and this is just the usual Heisenberg equation of motion. You work it out, dq of dt is p over m, same as before, and then so we get the same thing. Our position observable at time t equals 0 plus something like velocity, although this is already observable, and this is, kind of hokey formal way of doing it, but really we should apply the unitary group of time translations to get the same thing. Okay, but there's an issue here. If we've got a generally covariant system, which I'm just going to define as a system that doesn't have this neat parameterization and a decomposition into time and a configuration space, an instantaneous configuration space, if you like. If we don't have that, then we're not going to really be able to talk about this parameter tour in any meaningful sense, or at least it's going to be very difficult. So what do we do about that? Gambini, Porto, Pullin, and Tortorolo suggest that we promote these partial observables to one-parameter families of operators, as I just said, but to remove the dependence of these families on this unphysical parameter, we're going to integrate over all tau. So that's going to get rid of any mention of that in our predictions. So we're going to replace the condition, given that the time is tau, by this, given that some observable that doesn't depend on t takes a value in some interval delta, some Borel set. So in this formulation of ordinary quantum mechanics, we're going to ask, what is the probability that the partial observable QB takes a value b in delta, which should not be in A, given that QA has a value in delta, obviously the b's and a's meeting there. And this gives us conditional probabilities that are time independent. And this is a horrible sketch of their view. There's a lot more to say here. It's inspired by a great paper of Page and Wouters from 1983. I think it's evolution without evolution principle. Anyway, so just going to go into a toy model here. So
is a toy model only for your first strategy?
Yes.
Right, not okay.
Yeah, so we're just talking about option 1 at the moment. This is how we're going to eliminate time. So all I've done is add another particle. Everything else is exactly the same. And we're going to use the location of this particle A to predict the location of particle B. So in ordinary quantum mechanics, this thing's, we're just going to take the tensor product of two copies of the Hilbert space for each particle, of course. The state is going to be a density operator. We can write that as the tensor. And the condition that QA takes value in delta at time t equals tau, we're just going to project onto that subspace in Hilbert space A and apply the identity in Hilbert space B. Likewise, for QB, we're going to leave Hilbert space A alone and just look at Hilbert space B. Here's the functional analysis definition. If you're not sure what I'm talking about. So we need conditional probabilities. Conditional probabilities in quantum mechanics are given by the Lüder's rule. So we condition our state, we project a density operator, and then normalize according to the trace of the property we observed. And so long as we restrict our projections in a suitable way to make sure that the condition, the probability of the condition given the condition is going to be 1. Jeremy tells me I could just let these commute, but I've written subspace inclusion. So given that the time is tau, at an instant we apply this rule. What do we get? So the probability that B is in delta at time tau, A is in delta prime at time tau. I've just applied the stuff from the previous slide. Here, we just get that. But here's the clever part. To remove the time dependence, we're just going to integrate over all tau. So this is a neat way to find the integral. We're going to integrate from minus infinity to plus infinity. And all being well, and in this case, all is well, we'll get a meaningful quantity that will go between 0 and 1. So what is it we're actually conditioning on here? So the suggestion seems to be that particle A is functioning as a clock. But after all, we've got ordinary quantum mechanics in the background. Shouldn't a clock provide some indication of the time? Some indication of t if we're going to replace time by this clock. So the usual expression of this is time shift covariance. And if t is an ideal clock observable, then that's just to say that we act on it with our evolution group, and it's just adding on the amount of time with which we've acted, if you like. So we can measure it twice. We get a measure of elapsed time. But of course, Q doesn't behave like this at all. Remember, it behaves more like the classical position. So, let's see how I'm doing for time. I think I'm just going to skip these slides. I'd be happy to talk about this in questions. In my dissertation, I have a few chapters about clock operators, worries about them and so on, but I'm just going to skip that. The second condition, the second option for how to interpret this condition just involves thinking about what sort of experiment would be relevant here. So I think really what's going on is QA just corresponds to the location of an event involving particle A. So we have two particles set up here, two detectors set up. A is sensitive to A only, B is sensitive to B only, and we prepare the system and states, and we wait for both detectors to fire. Maybe we could locate them in different rooms or something. And what we're doing with these conditional probabilities, really, although they don't depend on time, of course, is we're just choosing the spatial location of the dots for particle A, and using that to condition on the spatial location of the dot particle B. But of course, they're non-interacting systems. These are independent events. We're not going to get anything very interesting by conditioning in that way. Now, of course, this would not be the case with a less trivial model. That's definitely the case. But what I want to suggest is we can use an even simpler system as the toy model. This is a game we like to play as philosophers. why do quantum gravity when you can do undergraduate quantum mechanics? So we're going to get rid of our second particle, and we're just going to talk about a single particle. And so we're going to have our detection experiment. We're going to have a screen for reasons of convergence. It's not going to be the whole of space. And we're going to say that the particle is just certain to be located at this location. So it's like there's nothing else in the universe apart from the screen and the particle, and we're just going to wait until that particle down registers on the screen somewhere. So we've got a projector onto the screen at a time t, and a projector on some sub-region of the screen at time t. So we've got this relation of subspace inclusion. From that condition, this is the subspace. Okay, so we do the same trick again. At time t, we apply Luder's rule, and you just get this concatenation of projections. That's an erroneous extra t, sorry about that. And of course, these are projections at the same time. So we're just going to project down to the sub-region. That all cancels away, we just get this nice expression here. And then again, we're just going to integrate over all t in the same way, and just integrated this. I'm sorry, I've added an a for no particular reason. So now we're going to define this expression we're going to use this expression rather to define an operator, two operators. And the way we're going to do that is like this. Like any operator, we just need to specify, well, with respect to some basis, but essentially we just specify what it does to a vector and what the inner product of that is. So here's a sort of formal expression where I've just copied down a bit from the last page in a bit more exact language. It would be this. And this is going to be an operator, a bounded operator when the limit converges. And for the free particle, it's fine, we can do that. We can define this on the whole of the space. Brunetti and Friedenhagen and Hogue consider this operator as the maximum element of a net of operators defined on temporal intervals. So these are a whole series of these things. This operator here corresponds to detection at the screen at some time. We're leaving the system forever, and at some time it's going to detect the particle. Here, you can think of these as being related to detection at some time interval. And they define a normalized version of this, which does make sense as POVMs, something that is, so in a POVM, we map here our temporal intervals to operators on the Hilbert space. Here they're positive operators rather than projections. So they've got this nifty normalization procedure, which we could call operator normalization, where you consider the square root of this operator. It's positive, so it has a unique positive square root here. And you can see that if we take the inverse, sandwich this between two inverses, then when we consider the one that corresponds to all times in this sandwich, we're just going to get the identity back. Everything cancels, just get the identity back. So that's going to lead to the idea that the probability of the particle being detected at the screen, given that it is detected at the screen, is 1, which is a nice property for a conditional probability to have, which actually turns out to be quite difficult to obtain with the POVM formalism. So by analogy, we're going to define a normalized POVM by the same means, sandwiching it between these inverse square roots. And now I'm just going to take the expression we had before for the conditional probability of detection in a sub-region, delta, given detection at some t within gamma. And I'm just going to insert a couple of identities here and here. Rephrase that and bring these into this, and we have an expression that looks very much like Luder's rule, except we've replaced the Luder's rule by the Luder's operation. This is sort of standard thing to consider in POVM formalism. And you can see that this is going to reduce to Luder's rule when these are projections, i.e. when b squared equals b, but the thing to remember here is that these b sigmas are not projections, so b squared is not equal to b. So what do we do to interpret these quantities, these observables, POVMs? So here we've got one that maps from subregions of the detector to these positive operators, normalized positive operator valued measure. So it applies only under the condition, it's conditional probability, applies only under the condition that the detector fires at some time t. That's what the conditionalization here represented, which we did like this. So this is answering questions of the form, what is the probability that the particle was detected in delta, given that it was detected in sigma? And the event POVM we defined earlier applies in the same way. We've mapped temporal instance to positive operators, and we've got an expression for conditional probability that has the interpretation, what is the probability that the particle was detected in sigma during some time interval, given that it was detected in sigma at some t. So this is a meaningful conditional probability that seems to have that interpretation. And note that these expressions have to use the Heisenberg picture. We're not really able to use this Schrödinger state because we've integrated over time. But we had to use this funny Luder's operation. Can we do this with Luder's rule proper? And I think we can. So let's return to our extended Hilbert space, which we constructed on our extended configuration space, R cross Q. So vectors in this space are functions of, or superpositions of functions of configuration space and time. So we can define a vector in this space in a time representation. So we've got a vector valued function of t, it's big psi. So at each instant we just define the value of this function to be the evolution for that instant tau of the vector instantaneous state little psi. So instead of thinking of one of these little psi guys as a family of states, a one parameter family of states in one Hilbert space, we're going to think of that same thing as a vector in the extended Hilbert space. So each pure state, each one of these instantaneous states lies in a copy of our usual Hilbert space, which is just the L2 functions of our configuration space, but now we're living in the L2 functions of the extended configuration space. So you can think of these as representing something like a career of a system. I'm hesitant to use the word history for obvious reasons, career. So what do we need to do to make sense of this formalism? Well, we've got an instantaneous state that lives in a copy of L2 of Q, labeled by tau, and we can define an inner product like this. This is the sort of active version, where we've got an orthonormal basis at time tau equals 0 here, and we're evolving forward vectors, but you could do a passive version as well. And then we're going to construct the extended Hilbert space from this as a continuous direct sum of instantaneous spaces. So that's going to have the consequence that the vectors at different times are going to be orthogonal. This is perfectly well defined. There's a paper by Nymark and Fomin where they lay this out. Everything I'm going to use in this talk is on the first page of the introduction. This is quite basic stuff from their point of view. So we can define an inner product here by integrating over our instantaneous inner products, which we can define like this. And we're going to have some sort of L2 condition on our vector valued functions. So we're not going to let all of these guys in. They're going to have to be bounded. 5 minutes. Okay, so what we find is that we can reconstruct everything we've done before. So any operator in an instantaneous Hilbert space defines an extended operator as follows. You just shove it between the inner products on the extended space and integrate through, so on. And we can define an extended trace which just reduces to the usual trace, and that's integrated over tau again. And so when we look at these conditional probabilities, we've just got exactly the same thing again. This is the expression from earlier, and this is what it looks like in the new formalism. We can add these in to give it the Ludus form, and we end up with something that looks exactly like a conditional probability in the non-extended theory, just with all these pluses to indicate that we're operating in extended Hilbert space. So we've really just recovered Ludus' rule. Now we're allowed to project onto times rather than just spatial regions. So we can project onto space-time regions, for example. And in this formalism, we can define a time PVM, not an event time PVM. This is just projecting onto intervals of time, like I said. And so we could do the time-dependent stuff in the same way. And we get back, so I'm going to rush it, we get back the instantaneous limit in the way you'd expect. Take the expectation value of an observable, some sort of epsilonic interval around t, take the limit, you get back exactly the same stuff. But note that we haven't applied the Hamiltonian constraint. The whole point was to reconstruct this theory in a way that resembled Ravelli's relativistic mechanics. So what we've seen is that ordinary quantum mechanics doesn't need to go to the extended, the physical Hilbert space, which we construct on top of the auxiliary, the extended space. And why is that? Well, in ordinary quantum mechanics, all the dynamical information is provided by the group of time translations generated by the Hamiltonian. So, I'm probably familiar with this. The time-dependent Schrödinger equation, so-called, is just the instantaneous version of the symmetry group. We just take the limit, go to the instant, and we've got a good old ordinary differential. This is a parameter. That's the Schrödinger equation. So if we only want to recover ordinary quantum mechanics, we should just stop here. We've got everything we need. But that doesn't get us very far in understanding this equation, which is what the whole point was. So if we want to do something along those lines, we're going to need a probabilistic interpretation that goes beyond ordinary quantum mechanics. And that entails a distinct notion of the state, a replacement of the trace, because Gleason's theorem tells us that these things go together. We've got a very closely knitted relationship between density operators and the trace. So what can we do? I'm going to try and let's do this. So given that we've got all these spectral projections of time, we can construct a time operator. It's the usual way by integrating over the spectral projections. This is an infinite dimensional projection now. So this is a quantization of the partial observable t, and it's got a conjugate, which we define in the usual way by just considering the operator that acts by differentiation in the representation where t acts by multiplication. And note that this is not the Hamiltonian in this case. So worries about unbounded Hamiltonians don't matter. So this is the quantization of the conjugate momentum of t. And note that now we could write the Schrödinger equation, or something that looks very much like the Schrödinger equation, by substituting this in here, taking our Hamiltonian and this. And interesting historical point, the time-dependent Schrödinger equation was first written by Dirac in 1927 in exactly this form. So how long have I realistically got?
Like a minute and a half.
Okay, so what do we need to make sense of this equation? Well, we're not going to be able to use a vector state or a density operator. You might think we could use an algebraic state, which is essentially an expectation value function on the algebra of observables. Here it's just going to be the bounded operators on a Hilbert space. We're not going to get that. What we're going to get is a weight, which is an unbounded positive linear functional, so that it's going to map some elements to infinity. And it's not going to have a representation as a density operator. Only a normal state admits such a representation. So here's some technical details. how you might go about doing that. This is Brunetti, Friedenhagen, and Hogue. And here's some information about how we could answer the same questions that we've been answering all the way through this talk in this formalism. So, pretty obviously, this is going to solve that equation, and we can just evaluate the same things in this formalism. But what we can do here that we couldn't do before is we can consider a condition that doesn't take up all of time. Remember, before we were just looking at a detector that was left for all of t to fire. Here we can condition on events that occupy disjoint space-time regions, even though those are orthogonal projections. So I'll just go through this slide and then stop. So this proposal pretty obviously generalizes to these covariance systems I was talking about, which don't have this nice parameterization, because we're just conditioning on the values taken by partial observable. So Brunetti, Friedenhagen, and Hogue explicitly constructs this for a scalar field and Friedman, Robertson, Walker spacetime. So you can condition on values of the radius and the scalar field. But I would urge a further interpretation in terms of events. So rather than just conditioning on the value of a single partial observable, if we consider two of these observables, if there's only two, then we sort of localize the system somehow with respect to observables. And if you sort of turn that around and regard the occurrence of events, say the detector firing, as providing a conditionalization that can apply in that way, then that's a way to give back the state. And in fact, it's necessary to specify an event in that sense to get a meaningful algebraic state out of this formalism, because the weight is unnormalized, but by specifying events, it's enough, and that is elements of the algebra of observables in the extended Hilbert space, that's enough to tie down the predictions so that you can get a state valuation on the remaining algebra. And note that this formalism doesn't require vector states, which invites the question, do we really need to go to the physical Hilbert space if we can do this in the auxiliary Hilbert space? So I'll stop there.
Yeah, there.
Shall we take the fact that that in this scheme you seem to need to rely on a screen detecting something, a detector detecting something else, which seems to put these kind of objects outside of the quantum description, imply that we should recover time only in a realm where we have already classical description for at least a collection of the objects? Should we give up the hope to have any notion of time in a fully quantum mechanical description of everything?
Well, I mean, so I think there's a few different questions. So first, I see what you mean. When I talk about detectors, it sounds as if there needs to be something external to the theory in order to make sense of it. But I think there is, if you're talking about a cosmology, why not just say these correlations between observables happen? It's a current fact that these correlations occur. Given that they occur, we can give further predictions.
They happen when we measure them.
Right, but you don't have to talk about measurement in this formalism, because you just have conditional probabilities.
When do these things happen? What is this notion of things happening?
I mean, I think it's a pretty fundamental notion that
it's not part of quantum mechanics without observers.
So yeah, I mean, in a sense, this would be a replacement for the notion of measurement. You're allowing that things can happen independently. I mean, if you think about what happens in an experiment, we set up a photosensitive screen, we just go away, we leave it, we come back, we find a detection. That's
also, but it's not described by the theory unless you put some kind of special rule for this measuring apparatus to be in a well-defined state.
Well, I mean, we've got a special conceptual role here for the events, in that we think that these conditional probabilities apply to them.
Yes,
with some more.
I have a really a simple-minded question.
Yeah.
So in the extended configuration space, right, we have t as a function of tau. Now, is it ever the case that t is not a strictly monotonic bijection of the real line? Because I would imagine that it wouldn't be, because then you would have two configurations corresponding to the same time, possibly. But on the other hand, if that's not the case, then it's not clear why we can't just interpret tau as the time parameter and t is just some transformation of it. It's just some function of time.
Yeah, so I've been discussing ordinary quantum mechanics because it's something we have a rough idea of how to interpret. So obviously that is a theory in which tau is going to be related to the time in the way you described, and so we can always just go back and check what the time is because it's still there somewhere in the formalism. But the idea of this generalization is that you can apply this to theories that don't have this neat parameterization, so they could have more complex relationships, and maybe wouldn't even be monotonic. I mean, you choose which observable you want to treat as time in this partial observable formalism. They're all on all fours.
Okay.
Brian, this is next.
I enjoyed the talk. Since you have some questions there, does that mean the audience can offer answers?
Please.
What I'm saying won't be plausible at this stage, I imagine, but maybe it will be then. I'll make it plausible in a few days. Your question, are direct observables really all that one can observe? I want to suggest the answer is no, because direct observables involve what commutes with first-class constraints individually, but those don't actually generate gauge transformations. And since there are fewer gauge transformations, there are more things that are invariant. So no, they're not all that one can observe.
So that was a quick preview of your talk.
To encourage you to come.